Hi everyone, I am Luis. I will introduce the paper Sell It and Forget It, Turkey ECC for Instant Integration. This work was in collaboration with Dimitri and Igor from Cryptocom in Russia, also with Billy and Jesus and me from Tampere University in Finland. This is the content where we will see in this presentation, where we will see our motivation, our methodology, and his implementation. We call this ECCKiila, and finally our conclusions. So in our motivation was because there have been a lot of improvement in elliptic curve cryptography, um, in particular in performance, constant time, exception-free, and formal verified implementation, but on the practice, integrating theoretic works into real-world deployment could generate some vulnerability that compromise the security. For instance, in OpenSSL, we can see many attacks like timing attack, even in the functional correctness has attacks, but some projects try to avoid these and reduce the features. I mean, they only take account the constant time and functional correctness. Even they take account few cores with these features, but in a large project like OpenSSL, where this project is a complete library, is not the best idea. So ECCKiila is a library that automates the implementation, testing, and integration of ECC stack for OpenSSL, GOST Engine, and NSS. In this figure, we can see the main components in ECCKiila. In curves, we have all the parameters for each curve. OP3 files, here we have the formulas. Also, we have some validation, the arithmetic, the lookup tables, and Mako. Mako have the templating that help us to generate the arithmetic for one of these projects. In our threat model, we included the timing attack. Kila means wage. Now, in this table, we can see all the cores that we have tested with ECCKiila, where we can see some cores has external model and internal model. So in this course, we need to map from Ballestras to Edwards, back and forth. We did all this process transparently. Also, we ECCKiila consider curves that doesn't belong to any standard or library, like the $1 million curve. So now we will see the elliptic curve layer in ECCKiila. Here in this layer is the point arithmetic, where it has a point operation like mixed point addition, projective point addition, projective point doubling. Here we use the exception-free formulas for Ballestras and Edwards, but in Ballestras we don't use exception-free formulas in the mixed point addition, because here there are a special case where the point at infinity has no representation in Ballestras. So the mixed point addition needs to catch this exception. We solve this asking if the y coordinate is 0. We did all this process in constant time. Now, to generate all this arithmetic, we generate this arithmetic based on the OP3 files. Now, an important operation in this layer is the point multiplication, where we implemented a variable point multiplication, where to represent the scalar, we use the regular nav method. With this method, we only need the half of the pre-computed values. Also, our implementation supports the variable window. In fixed point multiplication, we use the com method with interleaving. Also, we use the regular nav method, where this operation we try to do in a general way and independent of each architecture, where we calculate many parameters. One of these parameters is the size of the lookup table based on the size of the L1 cache. We did all this process in automatically. Now, in double point multiplication, we use WNAV combined with chamber trick. So we can share doublings, but the mainly advantage of this trick is that we can reduce the number of addition per scalar. So this operation is viable, but we use this operation in the digital signature verification, where all the inputs are public. Also, we implemented a linear path for variable and fixed point multiplication. Now, in the field arithmetic, we obtain this arithmetic from the fiat crypto, where to generate the arithmetic, we base on the form of the prime number. This is the formally verified implementation, because in the point arithmetic, we don't guarantee it has some formal verification. Now, so far, we have a functional arithmetic, but we also observe that research knows each detail in elliptic curves, but they don't have any skills or motivation to integrate all these things into a large project. However, the developers, they don't know each detail in elliptic curves to do some properly integration in the large project. So we try to do this with rigging. Rigging is a library that supports OpenSSL, NSS, and GOST Engine. In OpenSSL, ECCKiila generates a easy group structure where we design a simple wrappers for the variable point multiplication, fixed point multiplication, and double point multiplication. NSS is similar to OpenSSL. GOST Engine, here we only need the explicit parameters because it's independently from OpenSSL. Now, he has an example with ECCKiila for the Corp P384 in OpenSSL and NSS with these parameters, where we get the parameters from the JSON file. Then we generate the arithmetic with fiat crypto. We ask if the cofactor is equal to 1. If it is, we use the Ballestras model. Then we ask if the parameter A is in this range. If it is, we generate the curve arithmetic, where here we obtain the correct exception-free formula. Then we generate the fixed, variable, and double point multiplication. Here, ECCKiila generates a functional arithmetic, but considering its features. Now, to integrate this arithmetic in some project, we need to follow these 3 steps. Now, this is the result that we got with ECCKiila, where we have the baseline. The baseline is the original version, and the integration has the code from ECCKiila. We tested for the key generation, deriv, signature, and verification. So here we have 2 curves, SecP 256 K1 and the CryptoPro A. So in the signature, we can see that the curve from GOST has a good performance if we compare with the curve from OpenSSL. That's it, because GOST doesn't perform the inversion. Meanwhile, OpenSSL does this inversion. Also, we can see in this other curve from OpenSSL, we can see in the baseline for the for operation has a good performance, but this is because this curve has his implementation has many optimization. One of these optimization is that they use ABX instruction. But if we compare with this curve from GOST, the param set A, we can see we got a similar performance, but recall ECCKiila tried to generate all the arithmetic in a general way, but independent of its architecture. Now, this is our conclusion, where we conclude that our methodology produced excellent results, where ECCKiila generates code dynamically for any curve, like a standard curve for OpenSSL, NSS, and GOST. Also, we got a good performance if we compare with the previous version, where we obtain a good speed up to key generation, derivation, signature, and verification. Also, ECCKiila is flexible and powerful because we can add a new curve easily without increase the complexity into the project. Thank you.